At Waseda University, designers are working on a humanoid with a revolutionary sensitivity of touch. Delicate enough to hold an egg, strong enough to crack it. Its name is Wendy, and it's the first robot ever with such a soft touch. Each finger on Wendy's hands has yielding, compliant fingertips and a 6-axis force sensor that makes the task possible, if a little messy. Just recently, Wendy moved on to chopping cucumbers. Can sushi be far behind? At Tokyo University, another team is working on hand-eye coordination. See the ball, track it, grab it. They're experimenting with a high-speed vision chip. By connecting photodetectors directly into each pixel of the chip, it yields ultra-fast image processing. The chip can register the image and initiate a response in 1/1000th of a second, many times quicker than even the human brain. Processing speed is only one aspect of vision. Another is making sense of what we see, an activity that takes up most of our brain power. It's our 3D vision that orients us in space and allows us to move about in complex environments. But perceiving depth is not innate. It has to be learned through experience.
For us humans, vision is easy. In fact, we are probably one of the best vision machines that exists on the Earth. The world is three-dimensional, and we capture that information by the retina.
Robots today can see only in 2 dimensions.
In the case of TV cameras, we are capturing the environment onto 2-dimensional chip plane. Mathematically speaking, you projected 3-dimensional world onto 2-dimensional plane.
No robot is outfitted with true 3D vision. Fewer still have the brain power to understand what they see. But there is one mechanical creature that is beginning to make great strides. And it may be the first robot ever that knows how to rock. It's a humanoid called DB, short for Dynamic Brain. Years of artificial intelligence work suggest it's impossible to teach a robot everything it needs to know. But researchers like Stefan Scholl believe that the answer lies in building robots that can actually learn.
I think the key insight from our point of view is you cannot program these systems anymore. It is way too complicated. You have to find the methods, how they self-organize, how they learn autonomously, and how you bootstrap them basically from being more a little baby-like system and becoming a grown-up after a while.
For a robot to learn, it has to start with a goal. In this case, matching the rhythm of a drum beat. It hears the rhythm, then converts it to a series of computer instructions called algorithms. It then uses these instructions to guide its own arms. And if the rhythm changes, it makes an adjustment. In another test, DB tries to match the red ball's pattern of movement and to catch it with the yellow ball.
What you should see is hopefully that it gets better relatively quickly. It takes a moment, now it already knows where the target is.
As the red ball slows down, the robot must also slow its arm movement. What Scholl is working toward is a system that can reproduce complex human motion. See the action, map it, then mimic it. The next step is to adjust to changes along the way, then perhaps one day to really dance. It may be that our minds and bodies are just too complicated, that computers are just too different from the brain. Biological creatures like humans not only integrate a dizzying variety of sensory information, they do it with split-second timing. Control is distributed between the brain, spinal column, nerves, and muscles in ways we don't yet understand. To put it all together, hands, eyes, legs, movement, perception, all in one package, that is a formidable task. The artistry, the sheer control of a simple dance duet. This is a level of achievement that seems nearly impossible to duplicate in machines. And yet, that's the dream of many computer scientists.
Computers should be able to do complex thought, and I don't believe it'll be 100 or 200 years. I believe it would be in this century. I don't think you build a conscious robot by setting out to do so. The way in which you do something like that would be to build one that can evolve and let it evolve the intelligence it needs in the environment in which it's going to be placed, which is the way nature does it. That's the most powerful design technique we know of. And if we can use computers and simulation to create artificial environments and run that kind of process at high speed, we can imagine designing much better things than an engineer could with a drafting board.